Okay. Welcome to our September Ask a Physicist. Can you hear the shape of space? The first announcement that I have before we get started is our Beyond Center happy hour that is coming up. I think hopefully you saw it in the very beginning. It's October 6th. And it is going to be a social and educational event with a lecture and a discussion on what happened before the Big Bang. So it is in Tempe, space is limited. So if you're in town and interested, head over to our Beyond Center website to grab tickets for that. And then our next event after that is our October Ask a Physicist, which will be on October 24th. That's a week earlier than normal just because of Halloween. So still at 6 p.m. Mountain Standard Time. We will have guest presenter Nicole Younger-Halpern, and the topic is what if the Victorians had discovered quantum computing? So I will send out emails and announce on social media when the registration is open for that. And then lastly, just for tonight's webinar, if you have any questions at all during the talks, please submit them using the Q&A feature at the bottom of your screen, and we will get to questions at the end of the hour. So I think with that, I will hand it over to physicist and NASA astrobiologist and moderator for the evening, Cole Mathis.
Great, thanks, Jessica. Thanks everyone for being here. This is a really exciting topic tonight. We have two great speakers to talk about what is space-time and how we can understand what it is and what kind of observations we can make sense of. So I'm excited to hear what they have to say. I'm going to hand this over to Dr. Maulik Parikh, who's a professor in the physics department at Arizona State University, as well as in the Beyond Center for Fundamental Concepts in Science. So over to you.
Thanks, Cole. Can everybody hear me? All right, let me share my screen then. Okay, so can you hear the shape of space? That's a strange title for a talk. And so, well, let's get into it. Okay, this is a blue whale. Blue whales are not only the largest creature on Earth, but they're among the loudest. In fact, whales can make a sound, a very low-pitched sound, that is at about 185 decibels. So to put that into perspective, that's about the sound, the volume of 1,000 planes taking off at the same time, or a volcanic eruption. In fact, two blue whales that are on the opposite sides of the Atlantic Ocean can actually communicate with each other using effectively their own voice. It's really amazing. But here's the thing. Although it's an incredibly loud sound, we can't actually hear them. And that idea that we can't hear things except through specialized equipment is really the theme of today's talk. And that is that there are signals, the universe is awash with signals coming from all directions in space that we cannot detect with our ordinary human senses. And so some of those might be very dim. For example, there could be something very far away and we can't, the light is just too dim from it. And we need something special like the James Webb Telescope. Or it could be that it might be in a frequency range that we can't hear or we can't see, for example, X-rays. So we need special X-ray detectors to perceive signals that are in that part of the electromagnetic spectrum. But most excitingly, there are signals that are not light signals, that are not electromagnetic signals, and they don't correspond to any sense that we actually possess. So detecting those gives us effectively a new kind of sixth sense. And recently, one such method of detecting one such type of signal has been discovered, and these are called gravitational waves. And they were discovered in 2015. And what gravitational waves tell us is that the universe is full of invisible objects. These are objects that emit no light, and so if we were only reliant on electromagnetic light rays, we wouldn't see them at all. And they're making enormous sounds like those blue whales, but that we were previously unable to discern. And now we can finally detect them. So these are things like black holes or supernovas, or we'll talk more about those later. But that's the message that that there's ways of perceiving the universe that go beyond our senses, and in particular, gravitational waves are going to reveal things about the structure and nature of shape of space. Okay, so what do we mean by the shape of space? Well, it's a long story, which I don't have, which I'll give you an abbreviated version of. But Einstein basically realized that to make sense of gravity, we had to allow space to be, and space-time actually, to be flexible. So think of space like, all my metaphors are going to fail me here, but think of it like a sort of spandex fabric that you can stretch and squeeze, or maybe, well, that's only two-dimensional, so maybe it's a three-dimensional jello that can be compressed and kind of a blob that can change its shape effectively. So that's what space is, except it's invisible. So the thing that causes space to get curved and to change its shape is energy. So here, another metaphor is this trampoline. So we have here a two-dimensional trampoline, and you can see that if there was nobody jumping on this, the trampoline would be just flat. But because of the energy of the kids jumping on it, it's deformed. You can see that particularly on the right. So it's the same way in space, that if there was nothing in space, the sort of grid lines of space would just be nice horizontal and vertical lines that are at 90 degrees. But when there's energy, when there's mass, when there's it actually deforms the space and causes certain areas to get compressed and squeezed. And when that, so one of the things that really does deform space a lot are black holes. So black holes are enormously massive and dense objects that really kind of create havoc in space. And when there are two of them moving around, then, like say they're orbiting each other, then they really disrupt the space around them, and that disruption then propagates outwards like a ripple on a lake, and that's what a gravitational wave is. So we can see these disruptions of space that come about when two massive objects that are in motion. So here's an example of that. This is a simulation. These are two black holes, and you can see the grid lines of space, and they're moving around each other. They're orbiting, and ultimately they're going to coalesce or merge into one black hole. So as they come closer together, the space really gets shredded up, and out goes this wave, and which is a wave in space, off space, and it then passes years later through Earth. Okay, so that's what a gravitational wave is, and really it's a wave off space itself. It's not a wave. It's not that there's something in space that's waving. It's actually space itself that's waving. So what does that feel like? Well, so here, for example, is a ring of satellites, and when a gravitational wave passes through this ring, because it's stretching and squeezing the space between the satellites get deformed. So their relative positions to each other get deformed. So you can see this in this animation here, that the space between the satellites is stretching and squeezing as a gravitational wave passes by, and that's sort of causes the circle to turn into an ellipse, into an oscillating ellipse. Okay, so that was Einstein's prediction in 1916. And well, for 99 years, it remained just a theoretical prediction. But then on September 14th, 2015, at 9:50 and 45 seconds in Greenwich Mean Time, two gravitational wave detectors, specially designed detectors, where at Hanford, Washington, and Livingston, Louisiana, observed this. So before we get into this, let me explain what these detectors look like. Essentially, there are two mirrors, and the mirrors are, there's a laser that's bouncing in between the mirrors, and you can carefully sort of get an idea of the distance between the two mirrors. So think of the mirrors like those two satellites. As a gravitational wave passes through, it increases or decreases the distance between those mirrors. Okay, so the mirrors are originally 4 kilometers apart, and when a wave passes by, they expand or contract by a little bit. When I say little bit, I mean really little bit. It's less than 1,000th the size of the diameter of the nucleus of an atom. So that's an outrageous, it's amazing that that was actually detected. But here's what they found. So the way to read these plots is the horizontal axis is time, and the vertical axis is the change in the length of the mirror. So if the number goes up, if the graph goes up, that means that the mirror arms have gotten slightly longer than 4 kilometers. And if it goes down, it means they've shrunk a little bit beyond, to less than 4 kilometers as the wave passes through. And you can see, first of all, that the upper left picture on which was detected in Hanford, Washington, is exactly the same as the upper right picture in Livingston, Louisiana. Okay, so it's not exactly the same, but it's very similar. And so that's strange. What kind of object or what kind of source would create these two nearly identical looking signals at so far apart? And so the only explanation is that it must have come from space. And these signals are also about 7 milliseconds apart. And so the same signal was able to affect two different parts of the United States and 7 milliseconds apart. So it was clearly traveling around the speed of light. And so that's the signal. So what is it? Well, to figure out what it was, we basically go through a process of trial and error. So in the bottom two graphs, these are simulations, whereas the top ones are actual measurements. So in the bottom two graphs, you can see a prediction made by Einstein's theory and so people tried different things. Oh, let's see what the gravitational wave, how the two mirrors would be jostled by a wave that's emitted by, I don't know, two stars colliding or you know, a galaxy merging with another, whatever. So they tried different things, and here you can see finally that there's a signal on the bottom, a candidate signal, which looks like a pretty good fit to the signal that was actually detected, right? So the bottom ones are, the bottom graphs are simulations, and the top graphs are the actual measurements. So that's a pretty good fit. And this one corresponds to, so here's what we learned. So we learned that 1.3 billion years ago, in a galaxy far, far away, two black holes merged. And one of them weighed 36 times as much as our sun, and the other 29 times. You can figure out all of this from that signal. So 36 plus 29 is 65. And what happens is they formed a black hole that weighed only 62 times as much as our sun. So the original two black holes were total 65 times as much as our sun, but they only ended up weighing, at the end, there was only 62 times as much mass as our sun. So what happened to 3 times the mass of our sun? And the answer is, through E equals mc squared, it got turned into energy. And that energy was the energy of those powerful waves, gravitational waves that were emanated from the site of the collision. So just an estimate of how much energy there is here. So the amount of energy released in billion terawatt hours was about, and this enormous number with so many zeros that I don't even know what it's called, and how to say this in English. And meanwhile, just for context, humankind's total energy use over the next 1,000 years in the same units will be about 0.1. So this amount of energy released by these two black holes in about a half a second, what made them briefly produce more power than all the stars and all the galaxies in the entire universe in that one half a second. So it's, so that's very similar to those whales making a racket that we can't otherwise detect. And so now we've detected it. Okay, so it's sort of like this. So we can now detect a disturbance in the force, whereas previously we can't. Previously we were like Luke, was just oblivious to the gravitational wave passing by. All right. So gravitational waves are not actually sound; they're disturbances in the shape of space. But we can transform one kind of wave into another. There's actually no sound in space, right? So, sound is a pressure wave through a medium. But space is almost completely a vacuum. There's like 1 atom per cubic meter or something. So, so there are no actual sound waves in space, but all waves are sort of the same, and you can transform one into another. For example, when you have your phone and you stream your music to your car receiver, then the music goes by an electromagnetic wave and then gets transformed into a sound wave. So similarly, we can convert these gravitational waves into sound waves just so that we can visualize them, or rather hear them. And that's what we did. And here's what they sound like. So this is the sound of two black holes colliding. So I'd like you to turn your volumes up and listen very carefully, because remember, the whole thing is about half a second long. You hear that? There's a little chirp. It sounded like one of those Skype calls. But so that's the sound of two black holes colliding. That little chirp at the end is when the black hole has consumed the other black hole. That's what they heard in September 1950. Here's a pulsar. This one's annoying. The pulsar is a kind of a spinning star that spins very, very steadily, and that's why it produces this pure tone. So that's a single note coming from space, a single note in gravitational waves due to the very clean periodicity of the pulsar. And this is what a supernova explosion sounds like. The supernova is a massive star that blows up. And that sounds a bit like a whale, actually. And then finally, this is my favorite. This is a spinning black hole eating a neutron star. And so it's going to revolve around. Listen carefully. Like a helicopter or motorcycle. And then there's that chirp at the end. So it spins faster and faster as it approaches the black hole. And so that's why the motorcycles also seems to be picking up. And also the amplitude gets louder as it gets closer to the black hole. And finally, here is the sound of the Big Bang. So if we hear that, we've heard gravitational waves from the birth of the universe. This is sort of the infant cry of the baby universe. So I just want to sort of end here. We're in a new era in physics. We've basically discovered a new sense, and using gravitational waves, we're seeing all sorts of amazing astrophysics. But it might be even more interesting than that. And my own research is not in the signal, but it was in the noise, and whether the noise of gravitational waves, the sort of staticky noise, can tell us something fundamental about the nature of space-time. In particular, about the existence of hypothetical particles called gravitons. So if we detect these, we'll have learned that the signal that we're getting, that sound, is actually in a sense digital. So that's what I'm working on. It's a very exciting time in physics. Thank you. All right, on to you, Cynthia.
Maulik, I have a question before you get rid of those slides. Who's on the left in this picture?
I'm not sure. I think that's Yeah, I don't know. Is it Helen Ducash? I'm not sure.
Could be, I'm not sure. I was
Yeah.
curious if you knew.
Yeah, thank you.
So should I go ahead and share my screen, or Cole, do you
Yes.
want to take over for a minute?
Yeah, no, I think we can go on to you, Cindy, and then we can save some of these questions that came up for the end. There was only a couple in the chat there, but I think your talk might cover them. So next up, we've got Professor Cindy Keeler, who's a professor also in the physics department at Arizona State University.
All right, so I think I have correctly shared my screen here. Hopefully you guys can all see this okay? Okay. So today what I'm going to be talking about is the same basic question that Maulik just went over. Can we hear the shape of space-time? And what I'm going to talk a little bit more about is the mathematical side of it. So if we can detect the sounds, how does that tell us actually what the shape was? How much information do we get about the shape from what we can hear? And here I should probably put in quotes here, because as Maulik pointed out, the way that we actually do these detections usually involves very fancy equipment like a very large interferometer, or shortly as in within a decade, we will have the space antenna, LISA, the laser interferometer space antenna. So let me go ahead and get started here. I wanted to actually start by reminding ourselves about what information sound carries about instruments, about the shape of instruments themselves. So I'm going to start by talking about an idealized rectangular drum. What these pictures are over here is pictures of the shape that the drum makes. When you hit it with something, it'll make some shape, and then that shape will move. So for example, you can see that I've started this motion. Let me actually get them all four started here. So we can see that each one of these fluctuations, it's a different way that the surface of this rectangular drum can fluctuate. Because I'm assuming it's a drum, I'm assuming I've stretched the top of the drum over and then held it down at the edges. So you'll note that the edges, or the boundaries of the drum here, they never move. Only part that moves is the part that's in the middle. And we can also see this number here tells us the relative frequency, or what the pitch is of the sound that you hear. So if this one has a pitch, a frequency set at say 1 hertz, that would be very slow. So let's just give it units of 1, and I won't be specific about what they sound like. Then this one is going to fluctuate a little bit faster, and so it'll sound like a higher pitch. This one again is a little bit faster, and this one is faster still. So this would produce the highest pitch mode, and this would produce the lowest pitch mode. But these numbers here that give us the ratios between those different pitches, between those different frequencies that we hear, they depend on both the shape of the mode we're thinking about, the shape of how the drum is fluctuating, and on the edge of the drum. These modes were available because the edge of the drum is held fixed. It's not allowed to move. And there's only certain shapes that we can kick the drum in the middle. So we can tell that the frequency number here, it depends on how many ups and downs the drum has in each direction. So in this first picture here, there's just one place where it goes up and down before you get to the other edge. And that's true if you go across the narrow width or the long width. Either way, it just goes up and down once, either direction. Whereas this mode here, when I go left to right across this short distance, it goes up and down just once. But when I go this way across the long distance, it goes up and down twice. They're two different parts. One goes down while the other goes up, and vice versa. This one's very similar, except it's sideways, that it has one part that goes up and one that goes down. And this one actually has 2 each way. So that's why it's even a higher frequency. So if indeed we heard a sound that had each of these frequencies in it, it was built up out of these frequencies, we might be able to guess something about the shape that the drum came from. And in order to see that, let's actually take a look at the modes that you would get instead for a circular drum. So of course, most of the drums that we actually have in the world aren't square shaped. A square is a little bit of an unusual shape for a drum. Something like a circle is more common. And indeed, the frequencies that we get when we look at the fluctuations of the surface of a circular drum, they're different. So the ratio between this frequency, if I call this one 1 again, and then I ask how much higher pitched is this one, this is a different number. It's off, the sound is going to be higher pitched than this guy, but higher pitched by a different amount than when we had a square drum. So these ratios of frequencies, they depend on the shape of the drum itself or the shape of the edge of the drum. So the circle and the square have different apparent sounds that they make. And so we can ask the question of these frequencies, they give us sound pitches. So if I can listen to a bunch of sounds coming from a drum, is that enough information for me to tell you what the shape was originally? Or could I draw some other shape of drum that would sound just like a circle, just like the top of a circular drum? So this question was actually asked mathematically. Historically, this goes back even earlier than the reference I'm giving you guys here. This reference is from a famous mathematical paper written in 1966, asking the question, can one hear the shape of the drum? And as you can see, this was a question that Mark Katz was asking publicly to honor George Uhlenbeck. And this quote from Henri Poincaré here, it's telling us that physics doesn't just give us the occasion to ask about problems, it tells us how to give the solution. And so in this paper, Katz proposed the question of what can we find out about the shape of the drum? Is it unique if I tell you the frequencies, if I tell you the sound that that drum is going to make? And it actually took a while for this question to be answered. Some of the techniques were known even at the time in the 60s when this was first proposed. But a very solid answer was given in 1996, and the answer is no. You actually can't hear the shape of a drum. So this is, again, mathematical work due to Carolyn Gordon and David Webb, and this snapshot is from an article that they wrote to explain their results in the American Scientist. And what they found is that these two images, so off to the right here, we have two different images of a drum. And you'll note their shapes are different. Those two drums are not shaped the same way. They're shaped a little bit different from each other. But they make the same exact set of noises. They're, if you hit that drum and see all the different ways it can vibrate, it has the exact same set of possible frequencies or possible pitches it could make. At D1, that first drum, as D2. It doesn't matter which one you pick, even though their shapes are different. They still produce the same noise. So it's pretty natural to ask the question. Of course, these are both very funny looking drums. I don't think I've personally seen a drum with a top that looks like either one of these shapes. One can ask the question of, okay, well, is there any way to actually uniquely tell the shape of the drum? And it turns out I can if I give you some conditions about the drum. So if I tell you that the edges of my drum are smooth, the example that we had here, they have pointy edges. There are those triangle edges that are very pointy. And if I tell you that the drum is convex, if we look here again, there's indentations in the shape of both drums. So they're, rather than being a shape that's sort of round and that you can't, there's no indentations in it, both of these shapes are concave. They have little inset parts. But if I make sure that my drum is smooth and convex, and then I tell you all of the different noises that drum can make, then it turns out that the drum shape is unique. So I did want to make a little bit of a caveat here. The drums I've been talking about and the mathematical drums that these papers were all evaluating were very specialized, idealized drums. They were assuming that there was no friction and no loss of energy, and that the drum, once you make it vibrate, it would just keep vibrating in that same way forever. You could even see this in the pictures I was showing you, that those vibrations kept going and they didn't seem to slow down. But of course, real drums don't behave that way. Real drums lose energy to friction and to heat. And so they don't have normal modes, they have what are called quasi-normal modes, or the quasi means that they decay over time. So when you hit a drum and you watch it reverberate for a while, that reverberation gets smaller and smaller until eventually it damps out. You don't hear anything at all anymore. And these quasi-normal modes are much more like the physical modes that we might detect in the gravitational shape of space, as Maulik was talking about earlier. So just as a quick reminder from his talk, as we discussed, space-time itself has a shape, and its shape depends on the matter and the energy in the space. Our most extreme example of this is a black hole. This is actually a picture on the left here of the black hole at the center of our galaxy that the Event Horizon Telescope produced in 2019. So it's definitely an interesting era for black hole physics. We're now able to hear them and even see them, or see the light that they bend around them due to their extreme shape. So in addition to thinking about the shape of the geometry and how we could hear that, how we could do gravitational wave detections, there's lots of other fields that live in a curved space. So the electromagnetic field that allows photons to propagate so that you can see light in colors. The Higgs field that describes why we have mass for some of the particles in the Standard Model. Both of those also change depending on the shape of the space that they live in. And it turns out each one of these fields has a set of characteristic frequencies, just like the modes on the top of a drum. And around a black hole, these frequencies become quasi-normal modes. They decay. Why did they decay? Well, because stuff falls into black holes. So if I have put a fluctuation, I shine a bright light near the black hole, a bunch of that light is going to go away because it's going to fall into the black hole, and it'll never shine into any other observer who's outside of the black hole. They won't get to see it. So the total amount of fluctuation in the electromagnetic field is going to decrease over time. So we can ask the question of, if we can listen to the quasi-normal modes, can we actually reconstruct the shape of the space itself? Is just hearing these modes enough? And there's a couple of complications. So the first complication is that it turns out we need all quasi-normal modes to have a chance. So the papers that we were asking earlier, the mathematical papers talking about, can you hear the shape of a drum? They were assuming that you had information of all the possible frequencies that that drum could make. Realistically, when we measure the gravitational wave signal coming from collisions that happen in our universe, we're not going to get every possible frequency. We're going to get some. And it turns out there's another practical concern. The current ability of our detector for gravitational waves, the laser interferometer gravitational observatory called LIGO, it only hears the few lowest lying modes. So it's not finding what happens as you go up to higher frequencies, because they don't last long enough for us to hear them with that detector. There's also a more subtle issue, which is that gravity itself is nonlinear. Unlike the electromagnetic equations, which are linear, gravity is nonlinear. So you have to wait until you're in the regime where gravity is linear before we know how these quasi-normal modes could tell us about the shape of the space. And at least part of the interesting LIGO detections are times when dramatic events are happening, like the Big Bang, or a collision of two black holes, or any of these times when a black hole has eaten a thing, like the neutron star. All of those chirps that Maulik played for us earlier. It sounds like the black hole is a baby bird that's eating something and being happy about it. All of those times when it does that, those are all times when gravity is behaving nonlinear in that region where the chirp is happening. So only before and after the chirp can we hope to use the data to try to understand the shape of the space. But there's some bright sides too, which is that if we can hear many of these modes, we can actually learn not just about the shape of the space, but about fields that might live on top of it, such as the electromagnetic field, for example. And we might be able to reconstruct what's called the partition function for those shapes. So I think the conclusion that I have to answer this question right now, can we hear the shape of space-time? Not completely, but we can certainly hear things about the shape of space by listening. We can learn about it if we open our ears or our gravitational antennas, as the case may be. So thank you. That's what I have for you guys today.
Great. Thank you so much, Cindy. That was really great. I learned a lot. So there's some questions that we've got in the chat, and there's some questions that people sent in ahead of time. So I'm just going to pull those up really quickly. I think some of them were addressed by your talk, so we'll just go over them. Sorry, one second. Right. So I think the questions that we got ahead of time, one of them is, what does a graviton sound like? Well, like I'm sure you would like to know. It wasn't one of the ones that you had recorded, and I'm guessing that is something that we might not be able to answer yet. Do you have anything to say there?
Yeah, so a graviton first of all, would be the hypothetical. So in quantum physics, we have this idea that all the forces are actually transmitted by particles. So for example, the electromagnetic force has an associated particle called a photon. And similarly, we presume, and this is a theoretical conjecture, that there's a particle also responsible for transmission of gravity. And that's my hypothetical particle is called a graviton. So just like a water wave is made up of lots and lots of droplets of water, we expect that a gravitational wave is in a way made up of lots of gravitons. So what would an individual, a solitary graviton sound like? So a single graviton would be like a very pure kind of fluctuation of a very, 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 very tiny fluctuation with perhaps a definite frequency in the maybe like a, well, yeah, in the wave, in the separation of the mirrors. But in reality, there would be, there's no way we could measure it. So you would have to have a gravitational wave detector the size of the solar system to detect an individual graviton. But the trick is that we don't actually have to detect individual gravitons to become aware of their existence. So if there are many of them, they combine to produce a kind of a staticky sound, and that's called the noise of the graviton. So there's a collective behavior. So even though we can't discern the individual, we can't detect an individual graviton, we can infer their presence from looking at the noise of gravitons. At least that's our claim, and subject my research.
That's great. Thank you. There's a related question, and maybe you've just answered it here from Megan, about what do we learn from that noise? What does it tell us about space-time?
Yeah, so if the noise turns out to be, well, actually, first of all, let me say that noise has been a great source of profound discovery in physics. It was actually an unexplained noise in a receiver that at AT&T that radio antenna at AT&T was the first. Well, they were getting some kind of static. They went and looked, and it was full of pigeon droppings. But even after they cleaned out the pigeon droppings, there was still this staticky noise which was coming from everywhere in the universe, and that turned out to be the microwave background from the Big Bang. So noise is a really key thing to look at, and here we would learn not about specific sources, but we would learn about the fundamental nature of space and time. So in particular, we would learn about what's called the quantum state of space-time. And space-time could be hot, and then we would have a particular kind of noise. But the bigger picture is that it would tell us that in a sense, space and time are pixelated. And they appear to us continuous, but there would be some kind of discrete digital nature to them, which is how all the other particles are. So right now we think of space as something continuous, but maybe if we were to stare at it really, really closely, we would see the individual pixels.
Great, thank you. Let's see, there was also a question. So I think you both addressed this in different ways, but I'll just let you both have a chance to add anything that you think may have been missed. what can we learn from LIGO's recording of gravitational waves? So it's obviously very exciting that we've been able to detect them in the first place, and that's sort of entering this new era. And Maulik, you just sort of spoke about how that might give us some insights into, the fundamental structure of space-time. But you've also sort of put bounds on the amount of energy released in some of these interactions between types of black holes. Are there other things in cosmology or in astrophysics that we'll be able to learn from measuring these gravitational waves? And I'll open that up to either of you.
Sure.
I'm muted. You go first.
Okay. Yeah, I mean, it's like having a whole new sense, right? It's a brave new universe out there that we are detecting. In particular, everything that is invisible, either because it's literally invisible, like a black hole, or because it's just too far away or too dim, is now suddenly detectable, perceivable. So there's this whole kind of ghostly world of invisible objects that we are seeing. So there's a lot to we've even the very first event that we found, the discovery of black holes, we were astonished at how big those black holes were. Nobody was expecting the black holes to be that size. One was, like 30 times the mass of the sun. They weren't expected to be that big. And so there were, so there's a question about black holes, but also we've learned about things like kilonovas, which are collisions of neutron stars, and that produce all the heavy elements of the periodic table, all these, things like gold and platinum and so on. They all come not from, it was sort of a mystery of where these atoms, these elements came from. And they actually come from the collision of these neutron stars, these very, very dense stars. They produce, like in the aftermath of one of these collisions, there was an entire planet worth of gold that was produced by as debris. So we've learned about the origins of the elements. We've learned about black holes, and of course, our greatest wish is to see the to detect the gravitational waves from the Big Bang, because that would tell us about the origin of the universe itself. So far, we haven't detected them. They're actually not that easy to detect.
I have a couple of things to add to that. So one of the things to add to it is gravitational waves, because it's this new sense in the way that Maulik has been talking about, it allows us to enter the era of multi-messenger astronomy. So we already were in that era a little bit because we could detect things like neutrinos together with light signals, like X-ray signals. But now that we can add in gravitational waves, it's a truly new way of observing events. And there have been cases where LIGO was able to observe an event, and also telescopes were able to see the same event. So we can answer questions like, yes, it appears that gravitational waves and photons or light waves travel with the same speed or very close to the same speed. The restriction on that is quite tight at this point. And that allows us to rule out some possible modifications that you might do to gravity, because some modifications would change that speed. I also think that it basically affects every piece of cosmological or astrophysical physics, all the way from the Big Bang to what happens with black holes today when they collide. For example, one of the very early papers from the LIGO consortium was when the first two black holes collided, they could calculate what the horizon event area was for both horizons before they collided. And then they could calculate what the event horizon area of the final black hole after they collided into one would be. And indeed, as it has to be from some black hole thermodynamics considerations, that event horizon area, the final one, was bigger than the sum of the first two. So the event horizon area is only going up in the same way that entropy only goes up. And some of these things we theoretically thought were true before, but to actually be able to see them is really powerful.
Yeah, that's a really great example.
I want to add still more to that question, because it's really a great question. So some of those sounds are, some of those gravitational waves are coming from right at the, in the end point of that chirp. when one black hole ate the other, there were really two black holes right next to each other, about to fuse into one another. And as Cindy said, that's a regime of, that's a example of a very strong gravity there. And so when gravity is very strong, we can really probe its true nature. And one of the things we'd like to learn is whether Einstein's theory of gravity is really the correct theory of gravity. String theory, so far we think it is, but string theory predicts that Einstein's gravity is only an approximate theory of gravity to the true theory of gravity. And there will be modifications to it that will show up, in these situations where gravity is very strong. So we would like to really analyze that, not just the few milliseconds where the black holes are merging. That contains, I think, some rich secrets.
Yeah, that's really great. I think somebody in the comments asked about how this connects to string theory. So maybe not a direct observation of it, but at least a test of sort of the limits of relativity that might point in that direction. There were a couple of questions as well about whether or not gravitational waves can be used to learn anything about dark matter, or maybe detect dark matter in some way. Is that something either of you can speak to?
I don't know of any examples of direct detection. Maulik, if you know of those, you should add in. But certainly it can give us some information about indirect information about it. Like, for example, there are ways you can't modify gravity, then that constrains what you need for dark matter in order to explain the galaxy curves that are the big evidence for it.
Yeah, so gravitational waves aren't there to exactly detect the shape of space, but only detect the changes in the shape of space. So dark matter is usually just sitting there as a clump, and we can use other techniques with gravity called gravitational lensing to infer the presence of dark matter. So those don't involve waves of gravity. Those involve light that's moving through this curved space. So gravitational waves themselves, so far as I know, are not really used to find dark matter, but gravity is.
Although, somebody may eventually come up with a way of using it that way. One other large piece of evidence for dark matter is about how galaxies move through each other. And I actually don't know if any of the upcoming gravitational wave observatories like LISA might be able to find interesting effects from galaxy collisions. Do either of you know about that? I think the frequency range may be wrong.
No.
No, I'm not sure, but it's an interesting prospect. It's sort of difficult to pre-specify all the uses of a new sense, So that's one thing that's really exciting about this era.
Yeah, I mean, the most exciting thing is finding something that we don't know what it is.
Yep. Maulik, there was a couple questions here about the sound of the Big Bang. Do you just want to talk about what that data was and sort of how it was collected and what you played there?
I wish that were data. That was just a simulation of what the Big Bang should sound like. In fact, all of those were simulations except the first one, the chirp of the two black holes eating each other, that was actually detected. And the other ones are all predictions of what we would hear.
Great. And somebody has left in the comments that Elsa Einstein was the woman on the left of the Grand Canyon there. Thanks for that. That's great. There's a question here for you, Cindy. Are there an infinite set of drum shapes that can produce a given noise? So an inverse problem sort of question.
That's actually a really great question that it turns out I don't know the answer to. I will tell you that mathematicians who have studied the problem, the drum example is a two-dimensional problem because the top of the drum is two-dimension. They've also now studied it in general dimensions and asking questions about what if we insist the curvature of the space is positive, or what if it's negative, or all sorts of different variations on the problem have been looked at. And I actually don't know if the number of shapes is infinite. The example I gave you guys was just a pair that gave you the same set of frequencies. And that was enough to answer the question, no, you can't tell the difference. But it's a good question about how much would you learn? Could you know that it's one of these five or something? And I'm not sure that the answer to that is known. I certainly don't know it, but the mathematical literature might.
Awesome, thank you. Let's see here. So Dennis asked, is shape being used metaphorically here unless you think space is an object as in the top of a drum? How would you two answer that question?
No, shape is an object.
Yeah, I think I have to say both. It's a little bit of a metaphor because when I think about the shape of the top of a drum, I'm thinking about how that drum fluctuates in the 3 dimensions that are around me. And so it has a place that it can move into. Space-time doesn't have a place it can move into. It can just change its shape individually. So you might want to think more about, imagine if you're living on the surface of an orange and the orange is rotting. So it's becoming more and more dimpled over time, but you're still on the surface of that orange. You don't really care about how the orange is moving in and out. You care about how its local shape is changing because it's starting to rot and fall apart. What person who's living on the surface of the orange and only sees how the shape is around them, that's more like us living in space-time than the surface of a drum going in. But yeah, I definitely say the metric is a physical object. The shape of the space-time is definitely a physical object. How do we know? We can hear it. We have, you just did.
Yeah, that's really great. It is tricky to get your head around this concept of the change in shape of space-time, but yeah, it's definitely a physical thing.
Well,
Our satellites are proof of
it's
that.
not that unfamiliar. We live on an orange, a blue orange, so there are things that we can figure out from if you were an ant or an amoeba that lived on Earth and never got to go and experience the 3rd dimension. There would be still things that would tell you that you're living on a curved space. Like if you go all the way around the world, you'd come back to where you were, which you couldn't do if the world was flat. There are other things that you can do. If you can
Draw a big triangle, its angles are more than
triangles,
180.
Yeah.
Right.
So
right.
There are ways to. It's called non-Euclidean geometry.
Great. Jordan has asked if there's a website that's got those sounds in case people want to listen to them again.
At least the LIGO signal is on LIGO's website. I don't know if they have any of those model signals on there. The one that was the 2 black holes, that's on their website.
Great. All right. Here's an interesting one. What effects would the acceleration and the expansion of the universe have on the sort of waves of space or these gravitational waves?
I think this one's for you, Maulik.
Okay, well, as the universe expands, the waves everything in it gets sort of stretched out, and the waves also get stretched out. So because they get stretched out, their frequency gets lower. So they go down in pitch. So the sounds of space-time will decrease in pitch, and if the expansion is accelerating, it'll go down in pitch faster and faster.
Great, and we actually have the opposite of question. What we're using these gravitational waves to learn about sort of the shape of space-time, will that place constraints on the expansionary effect of dark energy, or you guys have talked about how this will inform our cosmology? Are there obvious connections to how this will limit sort of what we expect the long-term fate of the universe to be?
I would think the way to address this would be to, if we could actually do a detection of the Big Bang sound, because exactly how that would sound now depends on how it happened and also on the history of space-time since then, which would address some of these questions like the rate of acceleration and whether it's increasing and so on.
Well, yeah, if the universe really has dark energy, which it appears to have, then what's going to happen? We can make a prediction about what the great future history of the universe will be. So, a trillion of years from now, the universe will look pretty much like the space-time version of the sphere. So it's called de Sitter space. But that's the prediction of having dark energy.
Great.
Sorry, there's actually another slight response kind of related that I think is worth bringing up. There are a couple of different ways you can form black holes. One of which we've seen happening. We've seen black holes forming from stars that collapse and the matter spins in and gets close enough together. Eventually it forms a black hole. But there may also be what are called primordial black holes that happen from fluctuations very early in the production of the universe. And I do think that Lisa should be able to see some signals from primordial black holes. Again, this wouldn't be a signal that has that natural chirp like when they hit each other. This would be more change in the background sound of the universe due to their presence being everywhere throughout the universe. So that's another way we might learn something about exactly how those what the population of primordial black holes looks like, if it is there. Tells us a bunch about the history of our universe, and that gives us some prognosis about where it's going to go in the future.
Great, thanks for that. So there's one more question. I think somebody was doing some research ahead of time that we got earlier, and I think it's a technical question about what is a squeezed state? What does that mean in this context? Cindy, do you want to answer that question, or Maulik?
I can answer it, but it's about his research, so I think he should.
Oh, wow. Yeah, there are different sort of, so quantum physics tells us that applied to gravity tells us that space-time isn't something definite. Not only is it not fixed, but there are little probabilistic fluctuations in it. And a squeeze state is one in which it has particularly pronounced fluctuations, because so they're maybe the easiest one to observe because they'd be very noisy. So if the state of the gravitational field is the so-called squeeze state, the term comes from field of quantum optics, then we would have our best chance of detecting graviton noise. But I do want to, in the last 2 minutes, address this question about that everybody's puzzled by, which is, if the universe is everything that exists, what can it mean to say it expands?
Yeah.
So we have to stop thinking outside our universe, because the universe is all that it exists, and we can talk about expansion without expanding into something. So first of all, just imagine, the easiest way to do that, to visualize that, is imagine a two-dimensional universe instead of a three-dimensional. So it's a flat plane. And imagine also that that universe is infinite. So it's an infinite sheet of paper that goes off in all directions. Now, what is it expanding into? Well, so now imagine that on this universe, you've drawn a grid. On this two-dimensional sheet, you've drawn a grid where everything is, all the grid marks are, I don't know, a kilometer apart. And then with time, and so at each intersection, there may be a galaxy. And then with time, the whole grid is expanding. That doesn't mean that the universe is expanding into something else, because it's an infinite space. It's just, the grid is just stretching. And all points are getting further and further away from all other points. And so that's what it means to say that the universe expands. You didn't need to refer to an extra dimension or some ambient space that it expands into. You can just have the space itself stretch. And it's very hard to think of it like that, because we're so used to thinking of 3 dimensions and embedding whatever sheet, whatever a 2-dimensional surface or whatever in that 3 dimensions. But without leaving the 2 dimensions, you could tell in this 2-dimensional universe that it's expanding. Okay, so that's the example that you can try to think about.
Yeah, I appreciate that. It's always good to spend some more time trying to build some kind of intuition for what's being said here. It is hard to think of, the experiments you do with like springs and a sheet. You're always outside of it, and so thinking. Unfortunately, Dennis is not convinced, but hopefully he'll get there. Yeah. I think that's all we've got time for. Jessica, are there any last announcements? Otherwise, I think we can say goodbye. Thanks again, Cindy and Maulik. This very exciting, very interesting topic. And thanks for spending the time to share with us.
I do actually have one quick plug for the upcoming talk. It sounds like Nicole Younger-Halpern will be your presenter coming up next time. So I've heard her speak before. She's excellent. I think you'll enjoy it. And I did want to say, I think it's a little weird that you've decided Halloween is too scary for quantum computing, but it should be a good talk nonetheless.
Yeah.